Boa tarde a todos. Grand prazer participar deste webinar. I'm going to speak in English, though. And the topic I want to talk about is the scientific basis of enhanced rock weathering and some practical implications, particularly for Brazil and the application of enhanced rock weathering in Brazil. Let me just get my... Oops, there we go. So I'm going to talk first of all about why we need enhanced rock weathering. I'll then move into the scientific basis in a bit more detail, and then talk about the practical details about how this is achieved in Brazil. So it goes back to the COP conferences, and COP21 in Paris committed to a 1.5 degree increase in global temperature. And it recognized that we have to use a very wide range of tools to achieve this. We not only have to reduce CO2 emissions, but we have to remove CO2 from the atmosphere. After that COP, there was a commitment to increase soil carbon contents by 0.4% or 4 per mil. And this was achieved, or to be achieved, mainly by increasing the amount of soil organic matter that's in the soil, the organic matter content of the soil. Importantly, though, we need to address the soil carbonate content, because carbonate is permanent when it's taken out of the biological carbon cycle, whereas organic matter turns over and decomposes, is respired, and can re-enter the atmosphere. So COP is really important for this. COP21 started that 4 per mil target, but COP26 in Glasgow, UK in 2021 really was the green light for starting of the enhanced rock weathering industry. It was the COP where it was agreed that we had to do this on a very large scale. And what will be really interesting is to see what happens at COP30 in Belém and what consequences there may be from that particular conference. We will see. The reason why we need this is when we look at the carbon cycle, we can see that this is dominated by organic carbon and biological controls. So we have exchange between the ocean and the atmosphere, and between the land, where there's a coupled vegetation soil system, in the atmosphere. And we've got the important things here is to note that in the atmosphere, the stock of carbon is 730 gigatons, and the amount through respiration in the plant soil system is 120. So in theory, in 6 years, an amount of carbon equivalent to all that is present in the atmosphere passes through the coupled plant soil system. And that gives us an opportunity, because we know how to manage plants, we know how to manage soils. And so if we want a quick win in trying to reduce atmospheric CO2, taking carbon out of the atmosphere, if we can intercept that cycle in the plant soil system and retain more of the carbon in the soil, then we can break away and start to reduce the atmospheric CO2 content. So the key to doing this is taking carbon out of the biological carbon cycle, and we have to think of how we can do this. So this is where enhanced rock weathering comes in, because this is something which has been known for a long time by geologists. It's a phenomenon where the weathering of silicate rocks that takes place as a consequence of the Earth's atmosphere and interacting with the Earth's atmosphere. It is known that this takes CO2 from the atmosphere, and it is known that this has taken place throughout geological time. At the same time, this weathering releases nutrients for crop growth: potassium, magnesium, silicon, trace elements. So it supports the plant life that there is on the continental crust of the Earth. These phenomena combine. The weathering gives the opportunity to reduce dependency on chemical fertilizers, and it gives the opportunity to remove atmospheric CO2. So enhanced rock weathering has two benefits that we need to take into account. And we'll hear about these from other speakers as we go through the webinar today. So what is the scientific basis of enhanced rock weathering? Well, we go back to Golditch and the pioneering work by Golditch in 1938, who was one of the first to articulate this and write it down. We can see that the minerals which are associated with higher temperature rocks, igneous rocks like olivine and the plagioclase, calcium plagioclase, these are the ones which are least resistant to weathering. They weather most rapidly. And as we work our way down here, there's a sequence. And we end up with the quartz as the most resistant of the minerals that are formed in igneous rocks as primary rock forming minerals. This was empirically observed and recorded by Golditch. In the process, this is where the nutrients come from as well, because we can see the magnesium, iron, and calcium, and then magnesium, iron, and potassium being released. The elements change as you get further down the sequence. Calcium and sodium from the plagioclasers, and then potassium from K feldspar and muscovite. And of course, quartz itself is non-reactive in this weathering sequence. Overall, we can see a generalized reaction of fresh silicate rock plus water plus CO2 going to soil. This is how soil is formed. The mineralogical composition of soil is formed in this way, with cations released and bicarbonate released. Well, where do these go? Sometimes, if the chemistry of the soil is right and the rainfall and other conditions are right, we can form what are called pedogenic carbonates. These are carbonates which form in soils and they take carbon out of the biological system and it is then captured in the calcium carbonate. So the calcium would come from the silicate minerals and the carbon would come from the plants that are growing there. Where do we find these pedogenic carbonates? Pedogenic, that means they formed in the soil. They are well known. They've been particularly well studied in the United States, and they tend to occur in soils in locations where the rainfall is less than 700 millimeters per year. So they are in the western part of the United States, where the rainfall is low, to the eastern part of the United States, where rainfall is higher. Then you don't get them. They don't form. The soil scientist Jenny noticed that as you get greater depth, as you get greater rainfall, I should say, with greater rainfall, then you get greater depth to the carbonate horizon. So with 75 centimeters of rain, 75 centimeters depth, but by the time you get to 100 centimeters of rain, it's maybe 125, 125 centimeters depth. Most soil surveys in the Northern Hemisphere only go to 1 meter depth. So these are often ignored, these pedogenic carbonates. A more recent study looked at this in more detail and again emphasized that 95% of pedogenic carbonates occur with rainfall less than 700 millimeters per year. And again, 95% or more are found within a meter of the soil surface. There may be some bias in this to North American studies, but let's have a look at what they look like. This is a soil profile in Calgary in Canada. And here in that soil profile, you can see a pebble with the carbonate that's formed, newly formed carbonate by water coming down through the soil profile, dripping off the bottom of the pebble and precipitating calcium carbonate. So we need to know how quickly these things form, and they form in urban soils as well as in agricultural soils and in natural soils, in prairie environments. But we've actually been able to measure it in urban soils. We've actually been able to measure an increase in the calcium carbonate content of an urban soil that corresponds to the removal of 85 tons of CO2 per hectare annually. This is an enormous increase in the soil carbon content. It's 20 tons carbon per hectare per year. And it's by dating it using carbon dating, we're able to show it's modern carbon. So it's unambiguous that this is something which can happen extremely quickly when you've got the right chemistry of the soil. Compare 3.6 tons of carbon per hectare per year through the establishment of new woodlands. So soil carbonates can form extremely quickly when the conditions are right. And we can look at the plants as the source of the CO2. This has been known for many, many years as a way of determining how vegetation has changed in environments where carbonates occur in the soil. And we can think of this as CO2 being taken up by photosynthesis. As much carbon is exuded from the roots as there is in the tissue of the plant above ground. That carbon that's exuded from the roots is dominated by organic acids. And these decompose very rapidly. The microbial systems in the soil will decompose these organic acids. And the bottom line is that they end up as carbon dioxide and water. Some of the carbon dioxide partitions into the water to give carbonic acid. That then can react with calcium silicate minerals, and we have a simplified reaction giving us calcium carbonate and silicic acid in solution. So we can see here plants acting as a CO2 pump. And very, very simply put, if that plant is growing on a silicate rock, reacting with water and CO2, that will give us soil, it'll give us cations, and it'll give us bicarbonate in solution. So that bicarbonate is important because it's taken out of the terrestrial biological system overall. It's removed and it goes into the inorganic system of groundwater and surface waters. If we look at Brazil and think about where pedogenic carbonates may occur in Brazil, looking at this rainfall map, it shows that actually there's not very much of Brazil where the rainfall is low enough. And we would expect rainfall to be below 700 meters and the carbonates to possibly form in the northeast of Brazil, which is not necessarily an area where there's a centre for agricultural production that is currently interesting for enhanced rock weathering. But we will see. That's something to keep an eye on in the future. So if we have carbonates only forming in a small part of Brazil, where does the carbonate that's produced by this process actually go? And here we can see evidence that it goes into groundwater. I'll come back to this later, but there's a really important study of the Serrajal aquifer in São Paulo state, which shows the importance of bicarbonate in the aquifer in basaltic rocks. We'll come back to that later. So now to think about some of the practical details of how this is achieved in Brazil. We go back to Golditch and we've now added some thermodynamics to this. The minerals have been given a discrete name for a member of the family, for olivine, pyroxene, amphibole, and biotite as a mica, anorthite and albite as the plagioclases. And underneath you can see here the free energy of the weathering reaction, which is the thermodynamic way of describing whether the reaction is going to happen or not. The numbers are all negative, which mean that the reaction will destroy the mineral that's named by weathering. And the more negative, the less stable the mineral. So we can see here that forsterite has a free energy of minus 17 kilojoules per gram atom, then minus 12, minus 13, minus 10, minus 7, minus 1.68, minus 0.55, minus 5.88 and minus 3. So they're all unstable, and that negative number matches precisely what Golditch observed so many years before. So we know from the science that these minerals are unstable in soils. We've got basalts at the top, which are dominated by the anorthite plagioclase, pyroxenes such as ensitite, diopside, and forsterite. Andesites are intermediate in the middle here, and then granites and granitic rocks with quartz, micas, albite, K-felspar, and muscovite in the more stable part of this diagram. Weathering rates are critical. This slide is for those of you who like to take photos of slides while people are talking, just to give you the sources of the data which I'm about to show you. And some recent data have been pulled together in the last 3 or 4 years that give a very, very comprehensive and internally consistent set of data for mineral dissolution rates, as the titles of the papers suggest. Hermanska et al. When we look at the weathering rates and using the data from that paper, we get the same sequence. But here, the numbers again are negative, and the smaller the number, the faster, because this is 10 to the power of minus 6.97 in this case. So the weathering rate will be fastest for wollastonite, for nepheline, for anorthite. So nepheline and wollastonite have added to the sequence because they're used in enhanced rock weathering. But forsterite, then ensitite, then tremolite, we see a trend. Okay, it's perturbed a little bit with biotite. But if we ignore the tremolite, that trend carries on through. For the feldspars, we've got a very, very clear trend in the plagioclase feldspars, again, working their way through with the most rapidly dissolving, most rapidly weathered near the top of this diagram and the least near the bottom of the diagram. So these are the relationships that we saw in the Golditch series, now expressed in terms of what's known about the thermodynamics on the previous slide and in the weathering rate on this slide. So it works as a scientific basis for why this works. If we put on some of the rocks which are available to us in Brazil, we've got phonolites, which are dominated by nepheline. We've got camofugites, which would have forsterite and feldspathoids like nepheline in them. We've got the basaltic rocks, which are in the middle. And then we've got dacite and granodiorite rocks, which are used. I've put glauconite in here because obviously glauconite is a rock that's mined in Brazil, and the problem with glauconite is that we don't really have good dissolution rate data for it. So glauconite In some sources has a very rapid dissolution rate, -4.8, and in others it might be like a mica around -11. We just don't know. That research needs to be done. So what does enhanced rock weathering do? Well, it has to enhance that natural weathering process that I've just been describing. How does it do that? Well, it's enhanced through artificial intervention. And that artificial intervention involves, first of all, a very careful choice of the rocks that are used. We need to know their mineralogical composition. So we need to work carefully on the geology of the rock, on the mineralogy and the petrology of the rock. Once we know that we've got the right sort of rock, we need to increase the reactive surface area of the rock. And that's done mechanically by grinding or milling the rock. And that turns it into a powder of the desired grain size. And it is then spread onto agricultural land. And once it's spread onto agricultural land and crops are growing, then Mother Nature takes over and we have the growth of the plants and the CO2 pump taking CO2 from the atmosphere and putting it into the soil where it becomes available for carbonate formation. But the scale of the problem is something we shouldn't underestimate. We've got net zero targets agreed and adopted by many governments, and they are extremely challenging, particularly with the growth of AI. The targets that you see stated in those in various websites and places where the discipline, if you like, of enhanced rock weathering is being promoted, they commonly include targets of 1 billion tons of CO2. And if we need to remove 1 billion tons of CO2, as I'll show you shortly, that typically requires 5 billion tons of basalt. So we do have a big problem. Where will we find 5 billion tons of basalt? And can we use other rocks as well as basalt as alternatives? And the answer, of course, is yes. When we look at the chemical composition of a rock, we're able to evaluate how much CO2 it can remove. And we can do this in two ways. Starting on a very conservative approach, we might look at carbonation here, a simple reaction. We might take calcium oxide, reacting with CO2 and working out, calculating the equivalent calcium carbonate content. So that stoichiometrically is a relatively simple reaction to work with. If we look at the enhanced rock weathering overall, we know that calcium, magnesium, sodium, and potassium are the participants that go into solution. So we need to take all four of those into account. We need to correct for any calcium that might be tied to sulfur in gypsum or in sulfate minerals. And we need to correct for phosphate, which is there as apatite, which again ties up calcium. Phil Remforth published this equation in 2019, and I'm going to use it in a few minutes. What I've done is I've taken 11 rock types from various studies of rocks used as remineralizers in Brazil. In the list here, basalt, dacite, schist, phonolite, granodiorite, some rocks which are not quite clear what exactly they are, but the source is from Lorenzo et al.'s paper. Verdeche, which is a glauconite-bearing rock, and then in the camphorite domain, mafuorite and ugandite. And I've calculated the CO2 removal as calcium carbonate and also using Phil Remforth's equation. And what do we get? Well, for calcium carbonate, here you can see a inverse trend. The more potassium that's in the rock, the less CO2 is taken out. If we use Phil Remforth's equation, we can include the red spots here, and we can see the black crosses are still in the same diagram in the same place, but they're at the bottom here because this is only going up to about 80 kilograms per ton, whereas now we can get up to over 500 kilograms a ton for a camphorite. And the camphorites are really the most effective in this respect because they have the greatest content of magnesium in particular. But all of these rocks have got some CO2 removal potential. Looking in more detail, though, we can look at the rock compositions in the context of the Instrucción Normativa 5, which is the governing regulation for rocks that can be used as remineralizers. And in these, to be acceptable in accordance with the regulations, then the sum of calcium, magnesium, and potassium oxides must be greater than 9%. So if we put that 9% line on this graphic here, this is the sum of calcium, magnesium, and potassium, we can see that those which would not be acceptable in that regulation tend to have low CO2 removal potential, whereas those which would be acceptable in this regulation, in the context of this regulation, including basalts and camphogites, clearly have the possibility of removing significant quantities of CO2 in terms of kilograms per tonne. So what is the potential? Well, when we think about Brazil's agricultural emissions, it's of the order of 500 million tonnes of CO2 per year. And yet there are targets to restore 30 million hectares of degraded pasture. So there are big numbers being talked about here in terms of agricultural practice, which could be aligned with enhanced rock weathering. Let us assume, though, we just work with 1 million hectares. And we might spread 5, 10, 20 or 40 tonnes per hectare. How much of that overall emission of 500 million tonnes per year could be captured? And I'm assuming we're spreading mafuite, or the camphogyte, on 1 million hectares. This is on the right-hand side here, 40, 20, 10 and 5. So 40, 20, 10 and 5. We can see that we could account for 40 tonnes per hectare. We could account for 4% of Brazil's agricultural CO2 emissions. That is only on 1 million hectares. The scale, if we go to 10 million hectares, then it goes up to 40%, of course. So it's got the possibility of being scaled and being extremely interesting. However, this doesn't consider the carbon cost of production or transport. And that's what I want to have a look at now. I want to have a look at the enhanced rock weathering pipeline, where we have 3 stages. We have the processing, mining and stockpiling of the material. It leaves the quarry and goes through transport to the farms where it's spread, and the land where it's spread. If there's rain, the plants will grow and the CO2 will go to the source solution. The first challenge in this is, what is the rock that you're mining? The second challenge is, where does the carbon go and how do you quantify it? And the third challenge, what is the carbon cost? Does it cost more carbon to move this around or than is recovered from the atmosphere, is removed from the atmosphere? Let's have a look at what you're mining. So I've already mentioned the great advantage that Brazil has by having a regulatory system that allows the use of crushed silicate rocks in agriculture, already set up and working well. So that's a great advantage. In this context, we'll look at basalt, which is most widely used, and we need to consider what basalt is. It is strictly defined chemically by the International Union of Geological Sciences using a TAS diagram. And in this field, which is coloured here, we've got basalt. We can also have diabase, then the English word dolerite that corresponds to diabase, and the rock type called gabbro. They all have the same chemical composition, but basalt was erupted through a volcano. Dolerite never made it to the surface, neither did diabase, didn't quite get there. Gabbro, it refers to the coarse-grained rock in the magma chambers which fed those basalt volcanoes. We can look at it at the scale, but we have to look at it at the right scale. Outcrop, hand specimen, in thin section under the microscope, you can see the different minerals there, and using scanning electron microscopy, you can see the minerals very clearly. The minerals in basaltic rocks are dominated by the calcium plagioclases, pyroxenes, olivines. But we also have in this diagram, we can see nepheline is there, we can see biotite on the right, amphiboles, sodium plagioclase and K-felspar and muscovite. So we've got granitic rocks on the right. And we can then put that weathering rate on, weathering quickly or weathering slowly, depending where you are in that diagram. Hence, basalt is interesting because it weathers fast. But you've got to identify your rock extremely carefully. And when you're reading in literature, unfortunately, many publications don't do this properly. And so you never really know what rock it is they actually used. Did they use basalt? Did they use something else? Were they sold basalt? The geological community is very used to this type of problem, and there are codes that relate to the declaration of mineral resources, and these clearly define what the rock type is. When dealing with the metal mining industry, we need to see the same thing in the enhanced rock weathering industry. So by adopting a reserves relating to CO2, we can then protect the investors in these systems and make sure that people who are putting money in understand what their reward is likely to be. What about where the carbon goes to? Well, in this case, it's simple because, as I said earlier, it goes into solution, and we're looking at bicarbonate. The interesting thing is that if there are no other anions present, then bicarbonate is the only anion that can counterbalance the cations, calcium, magnesium, sodium, potassium, that's released by weathering. So that's absolutely vital because they have to have an anion to counterbalance those cations. So where does that solution go? Well, in a simple cartoon, we can see some of it will evaporate, the water will evaporate, leaving solute behind. Some will flow along the surface to surface waters or through the soil in subsurface flow. Some will go to groundwater. In the UK, if you ask a hydrologist, they'll say, well, it's about 10% goes to groundwater. In Brazil, when I've spoken to hydrologists, it's about 50%. So we don't know. We need to get a handle on that in the particular system where we're working. Basalt, though, is an important aquifer. In São Paulo state, tens of millions of people drink groundwater from basalt aquifers. If you go to the supermarket, you're buying water that's come out of a basalt aquifer in São Paulo, if it's come from São Paulo. And when you look at the analysis, you can see bicarbonate is the dominant anion. So you know that bicarbonate is there in that aquifer. This paper by Didier Gassmans and co-authors is a really, really good description. It's the most important paper from outside the enhanced rock weathering community for supporting enhanced rock weathering, for demonstrating that basalt weathering gives you a bicarbonate-rich solution, groundwater solution. And it shows that the water is safe to drink. So we do need to understand the carbon flux of groundwater. We do need to take that into account, even though it's not considered so much in the global north. But the important point is that basalt provides drinking water for millions of people in Brazil, and there are no health problems associated with that, which is excellent news. Finally, to look at the carbon costs, I am nearly at the 5-minute point, I know, and nearly at the end of the presentation now. For the carbon cost, we've got two components. If we look back at this, we've got the constant fixed costs of the mine itself, and then we've got the cost of taking it to the customer, and we may have thousands of customers, each with a unique carbon cost for that distribution and the logistics of putting it into place. There's this fixed cost for a mine, which might look something like this, a lot of fixed plant and equipment for preparing the crushed rock. And these fixed installations are powered by electric power. And most of that electric power in Brazil is hydroelectric. So the carbon footprint at this stage is extremely low. It's only a few kilos of CO2, 3 or 4 kilos of CO2 per ton of rock, which is remarkable. When you get to the farm, though, you've got equipment that is powered by diesel, and you've got the equipment that the farmer has, some of which is homemade. So you've got a lot of different possibilities there, which need to be taken into account for the carbon cost. These are two connected systems, but they're different. And we would want to have a model for carbon life cycle analysis, which kept this constant for years, maybe minor changes as plant was updated. But this one here, you could have thousands of subset models here for each customer. So these need to be taken account of in the overall picture for the benefits of CO2 removal. And we need to remember that although people's immediate thought is that, well, grinding and crushing rocks is expensive in terms of carbon, the fact is it's electrical power that's being used in most installations, and that comes from renewable sources in Brazil. The carbon life cycle analysis, again, needs to be done with great care, and the professional practices involved in carbon life cycle analysis need to be taken fully into account, as do the geological ones. Well, we've already heard that enhanced rock weathering needs many disciplines. I haven't got as elegant a slide as the one that was shown earlier on by Marianne, but here I've added a few more besides, geology, geochemistry, engineering, mathematical modelling, agronomy, life cycle analysis, social sciences, and then all the rest. It's a big business. But in conclusion, I think the important thing to bear in mind, and as we'll hear in the talks which come later in this webinar, we've got a really important climate mitigation activity here. Enhanced rock weathering has got the potential to make a big difference relatively quickly to the CO2 content of the atmosphere. In this, Brazil is world leading. We have the first carbon credits that were given internationally, were given to InPlanet before Christmas last year. And the other thing which is absolutely vital here, which is unique to Brazil, is its regulatory framework for crushed rock remineralizers. The rest of the world can learn a lot from how this process takes place in Brazil. The amount of work that's needed, though, to meet this challenge with all those different disciplines and people working together as large teams is enormous. It's not to be underestimated. But the benefits are important because we see the benefits that go to the farmers. The farmers will benefit from improved yields and lower costs, as they may be able to reduce the cost of fertilizer inputs. And then the enhanced rock weathering industry itself benefits from the trade in CO2 once those credits have been awarded. Well, I hope I've given you a bit of insight into the science behind enhanced rock weathering. I'd like to thank you for your attention. See, a few questions have come in, and I'll be very happy to answer any questions now and later in the webinar. I will stop sharing to hand back to Veronica.
Hi, David. Thank you so much for that. It was great. Very interesting presentation. Yeah, we have a few questions from the audience. So the first one from Erica Macy. She was asking that since enhanced rock weathering also enhances sulfide mineral reactions that lead to acid rock drainage and metal leaching processes, how are these acid-base reactions implemented into the benefits versus harmful from enhanced rock weathering calculations?
Yeah, this is a really important question, and the what I would say is that you avoid using rocks with sulfide minerals in any quantity. So this is incompatible with enhanced rock weathering if the sulfide content is high. So from that point of view, near where I live, for example, we have coal mines with a lot of sulfide minerals in the coal mines. The acid mine drainage problem for that is really, really bad and very negative on the plants which grow on the spoil heaps from those mines. You would not use that material in any agricultural application. And the same probably goes for the wastes that come from sulfide mining. Although they have the potential for enhanced rock weathering, I would not consider those as being ideal for agricultural application.
Yeah, fair enough. Thank you. Another question from Andre now. He was asking about the Cannon's method. It's a method proposed by Kanath on Nature in the article Thermal Calcium Magnesium Exchange Reactions to Synthesize CO2 Removal Materials. I don't know if are you familiar with
Yeah.
that one?
Yeah, the not that particular paper, but I know there are a lot of papers describing ways of synthesizing new materials, and it is interesting. The difficulty I have with these is the energy cost of doing this, because it involves taking a mined material, then doing some cation exchange with a mined material, which is often a high temperature process. And the minute you start working with anything that is high temperature, then your energy costs are enormous. And so again, they can be used for particular applications. For example, I think they're extremely valuable for taking CO2 out of industrial process streams like flue gases, emissions from cement works and things like that. There is the place for that type of product. But in agriculture, I think the simplest solution is the best solution, and the simplest solution is to take a natural silicate rock that's had the minimum amount of processing.
That's good. Thank you so much. We're getting lots of questions, so I'm gonna try to like cherry pick some of them. Christina Larkin asked if is it a compelling argument for bicarbonate export from basalt weathering in Brazil, looking at the content in natural groundwaters. However, some argue that the acidic soils at the surface in Brazil might prohibit bicarbonate generation. If it's possible to reconcile these two views.
Yes, the pH of a lot of soils in Brazil is so low, 4.5 to 5, that in theory bicarbonate would not be stable. And this is why it's so interesting to see the carbonate dominating in the groundwater systems, because that carbonate has to be produced in the soil and then it descends. It's not produced in the aquifers, because the carbon has to come from the photosynthetic pathway of the plants which grow there. So we have a bit of a paradox here, and I think that we need to see research done to integrate an understanding of the fate of carbon in the soil system itself as a function of pH, and then the through drainage, what happens to form that carbon as carbonate in an aquifer. So at the moment, I don't think the hydrogeologists have really connected with enhanced rock weathering, but I think that there's an interesting study there, which I'd love to see the hydrogeologists lead on, to do carbon isotopes in the aquifers to really demonstrate what the source of that bicarbonate is.
Good, good, good. Next question from Christian. What is your opinion on the usage of serpentines for enhanced weathering projects aiming to sequester carbon?
Yeah, I think serpentines are certainly interesting. And what you have to be careful about is the possible presence of asbestiform minerals within them, because obviously we don't want to spread asbestos minerals on agricultural soil, nor do you want to handle them in the source. But I'm sure that there are some serpentines that could be used in this way. We'd have to check what the weathering rate was. We'd have to check what their thermodynamic stability was in the soil.
Yeah, okay. So next one, we have lots of questions. Jennifer asked, in Brazil, is Brazilian industry already paying carbon credits for organic carbon capture, for example, planting trees, as they are in the UK?
Ah, no, that I don't know, but I think it is possible. Someone else will have to answer that question. I can't answer, I'm afraid.
Okay. And last one, Alexander asked, how do you calculate environmental impacts of mining beyond CO2 emissions to ensure the whole process actually is positive to the environment?
Yeah, so if you carry out a carbon life cycle analysis in accordance with international protocols, then that will be taken into account. But it is quite difficult because the mining industry would need to provide that information in a way which some companies do and some companies don't. It depends on the how open they are in terms of their reporting in sustainability factors. And you need to have specific information about the operation as well, which sometimes is commercially sensitive. So it takes a long time and a lot of questions need to be asked, but it is possible to do. There's for the type of mining that is used is very often the mining that's used to produce construction aggregates, crushed rock for making roads, for making concrete, for making materials for building houses and cities. And those quarries can be managed in a way which is extremely benign environmentally, and they can be restored in ways which improve biodiversity and give many, many benefits to the local community. So from that point of view, focusing on the construction aggregate sector for the sourcing of the materials gives you the best results in terms of minimizing the impact on the environment.
Good. Okay, we have a couple more questions. I think we have time for that. Roberto, he's not an expert on the subject, and he was wondering the potential of Brazil in sequestering carbon from the atmosphere using basalt.
Well, it depends on the availability of the basalt, and this harkens back to the earlier question because there's an existing industry which is very large, particularly in São Paulo state where basalt is mined widely. I haven't got the figures in my head, but I think we did some estimates which showed that there was the possibility using existing mines of removing many tens of millions of tons of CO2 per year. So the potential is significant without any new mines.
Okay, next one by Utku. They were asking if the mineral dissolution via carbonic acids versus organic acids, and how do you quantify this?
Yeah, well, organic acids will accelerate the weathering. So this is what the plant root exudates are putting into the soil. Acids like citrate, citric acid, oxalic acid, they will accelerate the weathering, but they are inherently unstable. And so they will decompose rapidly to give bicarbonate because they're used as substrate by the microbes that live in the soil. And so they rapidly disappear.
Good, good. Okay, last one from the chat. From Vedanta, they're asking if there's any carbonic acid forming by the interaction of CO2 and rainwater.
CO2 and rainwater. There's a small amount, but the pH of rainwater is about 5. It depends on the pH of the rainwater, which varies geographically, and the proximity to the ocean would have an effect on that as well.
Okay, now I have a question. I'm gonna put myself ahead of everyone. Yeah, I just wanted to know your expert opinion. What do you think is a realistic timeline for the CDR potential of enhanced weathering? When do you think we'll actually see enhanced weathering meeting like the targets for net zero?
the rate limiting step is going to be the availability of the rock and making sure that that rock is moving out of the quarries and onto the land. And so, although I said that you could achieve a lot with the existing mining infrastructure, we probably need to improve that and to um, mobilize that industry to pay attention to this market, because at the moment it's a bit of a new phenomenon. Uh, and so the quarries which produce these rocks see a new customer, but they don't know how big a customer that customer is going to be. They're not going to make any new investments till they suddenly see these customers wanting to buy and commit to buying millions of tons of crushed rock per year. And then we would see a change. So this is probably going to take 4 or 5 years still to take off.